Hi, we're going to continue talking about phase diagrams. Um, I'm just put up a couple uh, really complicated diagrams from found on the internet for metals. Um, just as a reminder that there are um, applications, many applications of these tools, phase diagrams outside of geology, and we'll continue to look at really simple cases, which can be quite powerful actually for some geological applications. But these same principles apply to other fields of science as well. So before we get further, I wanted to address a question that came up um, in one of the last classes. The question was why? Why does this occur when you mix um, materials that the melting temperature goes down when there's a mixture? And it should say that this is not always the case, but when it is, which it often is, generally is, uh, it has to do with, you could think of it from in different perspectives. There's a thermodynamic perspective, but we don't really have the background at this point to to use to explain. But we can also think of it from just a sort of an atomistic approach. In this case, um, the pure compounds have uh, like a stable structure, like a strong bonding. There's arrangements of for example, an ice, molecule, you know, that it just fits really together nicely. So it's hard to break that up. It takes a lot of energy to break those bonds at a high melting temperature. So when you introduce another material, another some other elements, uh, those make it harder for that stable structure is less stable, and there's always going to be mixing of things that are next to each other. Um, if you think about like the fish tank where you've got a blue and a red side, dyed side, and then you just very gently release a sheet, from between them. They mix, so that the salt will get into the ice, and those bonds aren't able to hold on as well, and so the melting temperature goes down. But I mentioned that's not always the case. Here's an example of a mixture of gold and silver, and in this case, there is pretty much it's a gently curved line connecting the two. So this would be, um, one of gold or silver. This is gold or silver. Um, Nowhere is the melting temperature actually higher than those of the on the ends of the end members, as we call it, but it's more or less just a straight line connecting them. And the reason that does occur sometimes, and in this case, is that gold and silver can, there's like what we call a solid solution. Like they mix together very well. And so the fact that there's an atom of gold versus an atom of silver there doesn't really make much of a difference in terms of the strength of the bonds holding them together. And then there's other cases, where we put more than one thing together, and there's a whole bunch of intermediate compounds that can form at different compositions. So we saw a miniature version of this, but you can see it can get quite complicated, where there's all sorts of kind of topography on this melting on the liquidus here, because there's intermediate stages where here's a compound, right, and so when those fit together in a certain ratio, it's stable, makes it harder to melt, and so there's actually like a bump, make the melting temperature is higher in that region. So let's continue talking about sort of reviewing basically, or sort of filling in some gaps about the phase diagram we already looked at, just going over it again. And before we do that, I want to remind you that, well, maybe not remind, but when we're looking at phase diagrams, we're talking about equilibrium. It's an equilibrium thermodynamics. So what that means is that we're talking about what is stable, not necessarily, nothing to do about how long time scales. So how long it takes to stabilize or to reach equilibrium is a different question. So thermodynamics always deals with that question, like what is a stable thing. So a diamond is not is stable at high pressures, right? It's not actually stable at the surface, but it takes so long to decompose that it at Earth's surface that it seems perfectly stable. So there's plenty of cases where I guess I'm saying it's important to keep in mind when we look at these diagrams that limitation, that there's another branch that we're not going to get into called kinetics that deals with the rates of processes and how long things take to happen. So let's just work an example on one of these phase diagrams. So the question, what happens to the material at the conditions of the blue dot here as it's heated? We're going to heat it all the way up to 1200 degrees, okay? So in blue dots, we have, it's a coordinate. So it's saying, okay, this is about 150 degrees, and it's about a mix of 50-50, 50% A, 50% B, two solids. Okay, so as we heat it up, so we're in this field, okay? So then the question is, all right, so what are these, what does it mean to be here, okay? So I said we're a mixture, right? So we're a mix of A and B. So really you can think of this blue dot as representing stuff over here and stuff over here. And based on its position, that tells us the proportions, okay? So this is just another way to sort of think about this. We use the lever rule as we move blue back and forth to say what percent we have, but the stuff we have is composed of bits of A and bits of B. Okay, so it just says that at the bottom. So at the start, it's a mix of 50% solid A and 50% solid B. Okay, you might want to pause and think about these as I go through them. Okay, so at this point, nothing has changed except that the temperature's been raised by 100 degrees, about 250 degrees now. Okay, so now at the eutectic, or sorry, we're not. Now we have reached the point where liquid occur with eutectic composition, okay? So the E here is labeling, this point where the two liquidus curves come down, okay? So at this point, as we've said before, we're going to we're going to sit here for a while. If we're adding heat at a constant rate, it's going to be moving up constantly till this point, and then we're going to sit here for a while. Think of this like if you have a pot of ice water in the stove. That's stirred up really well. It's going to stay at 0 degrees until even though it's sitting on the hot stove, all the way until the last bit of ice melts. And then it's going to continue on to higher temperatures. Okay, so what happens here is we go from that process here, the equivalent of the ice melting, and here in this case, we go from this 50-50 mixture of solid A and B at a temperature just below this. We get to this point, and when we come out on the other side, what we're going to have is a mix of solid B, that's what's indicated by the orange dot, and liquid. Okay, and the amount we have of the two is going to be determined by the lever rule. Okay, so we can just roughly estimate that. Okay, so we're a lot closer to the eutectic point, the liquid side. Okay, so it's going to be majority liquid. It's, if these are, we got 1, 2, 3, 4, 5 units of this compared to a total of 6 1/3. Okay, so it's like basically like 5/6 liquid as we after we cross this. So it's going to take a while to melt. And let's see if we've got a little cue here. Sorry, this way. Okay, yeah, so the liquid is going to have this composition, just dropping this line down. So the question then, how much of the material melts at the eutectic before the temperature rises? Okay, so that's what we're going to determine with the lever rule. I've measured them here. You could use the units that are here. You could put a ruler on it and measure it in centimeters, inches. It doesn't matter. It's just the proportion. Okay, 78% melt. All right, so that's a lot of melting that was generated here all at the same temperature. 78% melt, and then it's going to be, the remainder is this solid B. So you might ask, okay, what disappeared to make that melt? So because the melt is richer in this component A than our overall composition, more this A stuff must have disappeared. Actually, all of it disappeared, right? Because at this point, once we cross, we only have solid B. This is what it says in this field, solid B and liquid. So all of the A went into this melt, but we also put some B in there as well, right? Because if we put only A in it, it would have had a composition over here, but it has a eutectic composition. So we disappeared all of the A that we had in some of the B, enough, whatever amount we needed to get this this particular composition. All right, so we continue now warming this up. Okay, so at this point, as we're adding heat, it actually is raising the temperature. And what we see is that we have a mix of solid B still, and then a liquid. But you can see as we move up that this position is moving to the right. So what's happening is we're taking some of the solid B gradually as we increase temperature, adding it to the liquid. So that's making the liquid composition move to the right towards the direction of eventually it's going to keep going all this way, right, to the right. Okay, what's happened with the liquid as temperature increases in this region? That's what we just talked about. Okay, temperature is increasing. The liquid is, as the B that's remaining, the bits of solid B that are remaining, as they become melting, this composition of the liquid is increasingly coming towards the original composition, right? And if we melt all of it, everything's melted now because we're in the liquidus, then we must have the same composition that we started with, 50% B, 50% A. So the liquid now, we're not quite there. It says 99% liquid and just less than 1% solid B. So we're almost there. It's a tiny bit of B left. and we cross the liquidus. Now we're all liquid, and we have that same 50-50 mix of A and B components in this liquid. Okay? So this is the question we sort of posed in the previous lecture. Why are granites and basalts the most common igneous rocks? So this shows and we explained that as okay, because whatever the mantle composition is, the liquid that forms, it forms at a eutectic composition. Okay, and that happens to be basalt composition. So that's the reason that as the mantle, so the mantle is kind of like down here, it melts a little bit. It doesn't. It sort of exists in one of these fields of solids plus this liquid, and it doesn't fully melt. So we don't end up with melt that is just like the mantle. We get a partial melt. So we take some of the liquid, then we remove it and send it up into the crust. We make crust out of that. Okay, so this is a. I just wanted to show you this picture. So this is on a ternary diagram. We get for a granite, same kind of thing. That eutectic composition is in. Sorry, for most of the crust, if you melt it, you get a composition that is a eutectic composition, kind of in this granite area versus in some other igneous rock area. And you can understand this ternary diagram sort of if you see. So we're looking down at the base of that, right? And we've got three components here. So you can imagine like in 2 dimensions, what we just looked at, each of these sides is one of these phase diagrams that looks just like this. And then so in three dimensions, there's an even lower point. And that's the point where these, well, actually it's probably more like 4, 5, 6 dimensions. But you get the picture. That's why these are so common, granites and basalts. Basalt's what the eutectic composition is of mantle melt. Granite, eutectic composition of crust. Okay, so there's another way to think about this. We talked about the composition of the first melt to form. Another way is is to think of it as the last melt to crystallize. So let's think about that. Let's think about a cooling situation. Okay, so we're going to just take the same. We're going to do everything backwards now. Okay, it all works the same going in reverse. So let's say, so you could take like a basalt liquid, okay, and fully liquid. Now let's cool it down and see what happens, okay? Okay, only one liquid present, 50% mix. I'm going to go a little bit faster because this is totally repeating myself, just in reverse motion, okay? So at this point, across the liquid, so a little bit of solid is going to occur. And that solid is going to be solid B. If we'd been a liquid over here, we would have made a little bit of solid A, but we're over on this side. We've got, just because of the shape of this, crystals of B are going to form. And because crystals of B form, the liquid that's remaining is going to have less B in it. So it's going to move to the left. It's going to move in the direction of A, okay? Continuing to happen. It's getting more and more B is coming out, more crystals of B are coming out, so the liquid is having less and less B in it. Proportionally, that means more and more A. We could use the lever rule at any point along here. Here we go. We come down here. At this point, we're going to have, right as we hit the sort of the solidus temperature, we're going to have only 78% of the melt left. And as we remove heat from this, that 78% melt is going to get smaller and smaller. as we stay at the same temperature. And components A and B are both going to crystallize out until we cross the solidus. We have a solid 50% of both. Okay, so here's the where we've, instead of components A and B, we're calling it diopside and anorthite. We saw this earlier this week, this diagram. And I want to talk a little bit about those implications of where the liquid composition was. So if we were over here at A, right, the crystals that come out it's going to be a basalt with anorthite crystals. If you were over here, it's going to be a liquid that has diopside crystals in it. Because a lot of times what happens is you're somewhere in this field of solid and liquid, and then there's an eruption to just empty the chamber out, and then you get the rapidly cooled basalt. It's just going to look black, and then there's going to be crystals in it because they were the ones that had formed earlier in the liquid. So this is a rock, an image of minerals. These are pyroxene minerals all around, but then in the crack here, kind of in the pore space, is plagioclase. Okay, so we can infer, looking through the microscope at this rock, we can infer that pyroxene formed before the plagioclase. So this would have been on the left side of the eutectic. Let's go back. Okay, so over here, diopside is a pyroxene. Okay, so in this case, we were cooling, we formed those diopside crystals, and then later on, in this case, it didn't erupt. It's a coarse grained rock that cooled more slowly underground. So we do form anorthite crystals after we cross the solidus here. So we see, in the end, we see both types of crystals, but we can tell the order looking at the microstructure. And then alternatively, here's a case from the other side of the eutectic where these blade-like black and white things, those are feldspars, plagioclase, and it formed first. So you see there was a bunch of those crystals, and then this big crystal grew over the top of everything. That's a pyroxene. So this would have been over here, like at point A, forming a plagioclase, anorthite, and then a pyroxene.